Welcome everybody to LLM Engineering Cohort 3 Session 5. And today we're going to finish up our module on the transformer, attention is all you need, by covering decoding. And we'll run into a number of trailheads today that will be really important. They're some of the most kind of important things that people aren't really sure how to think about today. How do you actually constrain the output of an LLM? How do you make sure it's good? How do you make sure it's not going to upset any of your customers or do anything that you don't want it to do? This is the essence of what we want to do when we're decoding. We want to do it right, we want to do it good, we want to do it correct for our application. So to really understand the nuts and bolts is going to help us when we build, ship, and share production LLM applications, which of course all of you are on the path to do, just like everybody here at AI Makerspace. So a couple of quick shout outs as we get started today. Who's been building, shipping, and sharing? Shout out to Aravind today, AVIP in Discord, crushing it, talking about Rag Builder. This is a custom thing built by Aravind. So this was really cool, and definitely if you didn't get a chance to check it out, go hop in the Discord and let us know what you thought. Give him some feedback on Rag Builder, help him continue to build, ship, and share. And if you've got something that you'd like to run a community session on, we'd always love to have you. Sarah would be happy to set it up. And we've got a number of rocking community sessions coming soon, so stay tuned. Also, quick shout out to Nalay. Just again, Nalay, you're just everywhere, man. You keep shipping everywhere. Coming to the Monday meetings too. Very cool. Couple shout outs too to the peer supporters, just following up with folks into the holiday, after the holiday. Shout out to Deb here. Shout out to Alan here, following up with breakout rooms. I love to see this. If you want to know more about what's going on around the community, I'm going to start limiting the amount that I share here. There's just one more thing I want to tell you guys about, and that's what Christos is trying to kind of get some momentum around. If you're looking for accountability in 2025, heading into the new year, kind of start going to the gym before it's time to go to the gym with your personal branding, with your sharing, then Christos, Steven, Mert, and Don, they meet us all on Mondays, and they're really, really pushing to try to get a little accountability group going. So if you're interested, come next Monday at 9 a.m. PT or DM me in Discord and let me know. I'm happy to get you linked up with these guys. They always have their hands in all these different projects throughout the community as well. Great little group to be connected with. This week, we're talking AG2. That's what we're building, shipping, and sharing. So if you're into multi-agent frameworks, come check it out. Today, again, we finished the module that we've been working on so far the whole time. We talked next token prediction. And by the end of this session, what we want to really get to the bottom of is we want to get to the bottom of decoding. We want to get to the bottom of predicting the next token. We want to get to the bottom of temperature. This is the one parameter that even people that only use Claude and ChatGPT and do prompting, this is like maybe the first thing that they'll sort of dig into the model and start playing with. What is it doing exactly? Yes, it sort of says you can be more creative or less creative, but how is that manifesting itself within the transform architecture we've learned so far? That's what we're going to learn today. Additionally, there are some emerging techniques, not quite best practice standards yet, but potential candidates for them, like speculative decoding that we'll talk about in the second half of class. And it turns out that when people talk about putting guardrails on LLMs, they're really talking about constraining what comes out of the things. And since we're talking all about what comes out, that's going to be well within our ballpark today. And we're going to talk about how to leverage NanoGPT to put guardrails on NanoGPT, to do speculative decoding, and to do some other cool stuff with the model. And we're going to kind of get into it today by doing a quick review. Now, the quick review is actually in this meme. So if this is all making sense to you already, then you should be pretty good to go for the discussions today. We'll talk Logits, we'll talk temperature, we'll talk decoding methods. This is going to like harken back to sort of Wiz's advent of code a little bit, a little leak code style action kind of stuff going on here. Then we'll talk speculative and we'll talk guardrails. So we got a nice little overview today of next token prediction. But first, let's kind of go and remind ourselves how we got here in the first place. LLMs predict the next token. They predict, in general, let's call it the most likely next token. The most likely of what? The most likely next token, like within some distribution of potential tokens. We're always generating a distribution, a probability distribution at the end of the day, from which we can sample a token. Now, there's different ways we could use that distribution to sample a token, and some are more direct than others, as we'll see. Some are more sophisticated than others, as we'll see. But kind of just walking through this in a really simple step-by-step way. Before we even enter into the transformer, we're taking our words, our sequence, and we're tokenizing it, right? That's turning words into tokens. Once we have tokens, we put them into lists of numbers. That's the embedding process. The positional encoding process keeps track of word position within the context. The first thing we meet here is our little residual connection that goes to add norm. This is about not forgetting what we've already learned. On this first pass, it would be presumably the embedding representation and the positional encoding. That multi-head attention, 2 heads are better than 1. We spent a lot of time on attention last time. We want to attend to each token in the sequence and make sure we're listening to the right parts of the room to hear the conversation that's most relevant to us. The feed, the add and norm piece of this, the layer normalization, we're doing that residual connection. This is in the normalization is just to not have us overfit, right? The residual connection is really don't forget what you learned, and the normalization is don't overfit. As we head into the feed forward neural network, we're looking at the sequence kind of from another angle, right? We're sort of rotating the object in our hand on the pedestal and taking a little view of it. This is the encoder block, right? And then, of course, we're feeding this attention into the decoder block, which has gone through the same process. And then one more little feed forward add norm. After this add norm, we have our linear layer. Our linear layer is simply taking the raw scores or logits that we'll talk about today for each token in our vocabulary. It's creating those raw scores, those logits, and it's projecting the vector that we have coming out of our decoder block up. Finally, we have the softmax that converts the raw scores to a probability distribution. After the softmax, we have our distribution. We can sample the next token. Okay, so as we've talked about before, this is the GPT-style decoder. And today, it's important to sort of note, we're talking about decoding, right? But it's different than this decoder block, although it's not that different, right? Because we are doing the decoding here at the end, as we'll see. We have to sort of encode and embed, positional encoding, embedding into this encoder. And, we're encoding, we're embedding even right here. And even if we get rid of the encoder, we're still encoding and embedding here. And then we go through the decoder block and we finally have to decode at the end. So we're kind of going in to out when we use a GPT style, which we will be using pretty much exclusively from here, although you will see BERT style models come back in when we do things like reinforcement learning with human feedback later on. So this GPT style, one of the things that I'm going to do right now is I'm going to just flip this thing up on its head, because this is going to help us to use the visualization of the actual model we are concerned with today. And that model is the Nano GPT model, where at the top, it's actually the input. So we're putting our sequence of tokens in the top, and then we're getting our next token predicted out of the bottom. So instead of in, out, we're sort of going in. Instead of going in, out, we're going in, out. And then you can kind of see in this visualization, we have multiple blocks, whereas this is just one block. So we can start to now stack our decoder blocks in our head. And, at the bottom, we have this sort of next token prediction thing. Okay, so we want you to leverage this visualization today. We want you to think about each piece of the stack, because if you can really understand each piece of the stack, it's going to help you in literally everything you do with LLMs later. So let's talk about decoding. After we go through the decoder blocks, we need to decode. So what does this mean? Well, decoding could also mean allocating. Basically, what we're doing is we are taking that embedding representation and turning it back into natural language. Okay, so to do that, we have to sort of pick which piece we want to decode fully. We need to take what's coming out of the decoder block, and we need to select the next best token. And generally, when we do that, we're doing this soft maximum that we've talked about before. It's not the hard max, it's the soft max. And the reason is because when we do a soft max, we can just sample the distribution. We don't have to look through everything and pick the absolute maximum. If we zoom in on what's happening here in NanoGPT in this visualization, one of the things that's happening here is this is kind of the soft max piece here. We're taking the Logits and we're doing this soft max. There's actually two pieces here. There's this aggregation, and then there's the softmax. We'll kind of get into how one is more important than the other shortly. But right now, the other thing that you can understand is we can put all sorts of different heads on this thing. And since we flipped it upside down, it kind of looks like it's on the bottom, but it's still sort of the head. And the classic thing would be you could literally put a classifier head on this, and you could say, pick the next token directly by classification, right? So there's real deep connections to classical machine learning here. Now, when we select the next token, we're just selecting the softmax of these Logits. And so this is where it's important to understand, this is a super confusing word. What's a Logit? Well, it's hard to Google this and figure it out. Logit means logistic unit. A logistic unit, a logit, it's taking the log of the odds. Now, odds is just the ratio of a probability of an event occurring to the probability of the event not occurring. And, this sort of piece here that we can kind of see right here, this LM head weights piece. What this is this is sort of that linear projection layer we can visualize in the transformer, and it's helping us to get our information that we've attended to. We've got our sequence, we've got everything there, and it allows us to sort of project it into a space that is the same size as our vocabulary. So you see this is the size of the vocabulary by the number of tokens. Okay, so this is kind of that linear piece here. Again, find the raw scores or logits for each token in our vocab, and we kind of have to do this through this LM head weight projection. To think about logits, let's just do a simple example here. Okay, finish the sentence, right? High probability that we all know what it is. If it has a super high probability, that means there's very low surprise. It's very low probability of surprise. So if we think about the odds of something, probability of an event occurring versus the probability of an event not occurring, we can actually just literally take the log of both sides of this equation, And that's the Logits, okay? The log of the odds. So you might say like to be or not to be. Here, we're going to have like a really high score on our Logits for this token B, all right? Now, if I just came out of nowhere with some other way to finish this sentence, I'm going to get a really low score on Logits, like deep negative kind of thing. And, you know, you can sort of do the math, and it's fun to kind of do the math and to remind yourself of how to do the math here a little bit. Like if you said, well, if I have a very low Logit score and I want to play the sort of both ends of the spectrum game here, then I could sort of solve this equation for the odds, and the odds are going to be e to the negative infinity. They're going to be basically 0. It's almost like no shot that that's the next token. Whereas this one, it's going to give me a very high probability. Now, this technically would be an infinite probability, but you know, you kind of get the idea by looking at both ends of the spectrum. It's very high. And so we kind of generally want it to be a relatively high probability. You know, we kind of want the next token to be somewhat predictable. And we want the odds to be kind of up there. And if the odds are up there, then we're going to have this sort of idea that the Logits are kind of high, all right? And this is where temperature comes in. Because what temperature does is it basically allows us to either say, I want the next token to be super obvious, or I want it to be like way out there. And this is that sort of creativity thing. If you look at OpenAI's docs, this is what they say. They say lower values are more consistent, higher values more diverse and creative. Literally, temperature just divides the Logits, okay? And you can't have temperature of 0. Try it. They won't let you. Because you can't divide by 0, of course. And so if we have very small Logits, we're dividing by a very small number, that means we were very constrained. And it means we want it to be very predictable. And so the Logits go way up. For the Logits that are pretty big in the first place, they get ballooned up. Whereas if it's very big and we have this very creative thing, what happens is we're sort of dividing the big numbers by a big number, and we're also dividing every other number by kind of big number. And so we kind of get this normalization thing. So if I have this very high temperature, then I kind of get more of a uniform distribution, and I get more of that creativity, more of that random spark of insight in the next token. Whereas if I have a low temperature, to be or not to be, you know, it's really like, it's totally deterministic that this is going to be the next token. And so even just right there, you can start to see the beginnings of guardrails. And so like, again, if we're 100% sure, we want the odds of this next token to be quite high. And if we want things to be 100% predictable, we could use temperature to really drive the Logits in that direction, to really magnify the things that are most predictable by using a very low temperature. Now, regardless of what we do, when we're computing Logits, when we use temperature, at the end, we have to then take those Logits and we have to decode them. They're sort of in this coded embedding space language still. Again, how does the model predict after Logits, after temperature? Again, this is where the softmax comes in. Okay, so we've done the Logits thing, we've done the temperature thing. Now this aggregate, this is not actually softmax, this is just sort of part of the visualization, and it's, again, one of these nuances that we don't really have to worry about to get an intuition. This is really what's happening here, and this is how we want to think about the softmax, is it's really helping us to sample the distribution, and it's taking these negative infinity to plus infinity Logits, It's making them all positive. It's normalizing them. It's creating this nice probability distribution that once we have this thing, there's a lot of stuff we can do with it. For instance, we can use different, increasingly complex techniques to decide which one to pick, right? So once we have this distribution, we have all the tokens that we could possibly choose in front of us in a distribution with different probabilities. Which one should we pick? Well, that's kind of where some of the engineering is going to come in for some of your applications that you'll build out. Now, we can start with the simplest kind of thing, like the greedy sampling, right? What do you do if you're greedy? You just give me the thing, give me the thing. Just give me a thing. Just sample it. Boom, done. Assume it's normal, sample it, whatever, right? Or just straight sample the discrete distribution the way it is. And so, one example of what you could do here is you could do like the not soft max, the hard max, where you just always take the highest number. Sure, you could do that. Or you could do this sampling. And there's other ways that we can do sampling, right? This is like classic statistics 101 stuff. We could use the top however many we want, and then we could consider them in interesting ways. And we could have all sorts of other things come into play. You could even use another LLM to help you decide. Like, there's all sorts of things you could do here, but every single thing you do that's going to add complexity is going to add some level of cost, some level of additional compute, or it's going to add something that you might want to save for use elsewhere. Or we could not use a greedy method. We could use something that's a little bit more sophisticated, and this is called a beam search, where you sort of generate a bunch of potential different outputs and you see which one is the best. Again, it's sort of this nice intuitive thing that we can do. So the great thing about decoding is that you can kind of use your intuition to guide for your particular application. What does good look like? What does a great output look like? How could you actually constrain things programmatically to get those on a consistent basis? This is sort of the whole thing with guardrails, with ensuring that the things that are coming out of your LLM are good, they're correct. Now, there's this whole other field called like evaluation of LLM applications that you can sort of get around this decoding step, and you could sort of abstract it away a little bit, and you could rely on your evaluations instead. And that's something that we go into great depth in the AI engineering bootcamp. But this is like a sort of at the level of the LLM you can actually constrain. And so we're going to dig in at the level of the LLM with NanoGPT today. This is a great starting point. So Wiz is going to load this in, and we're going to be able to take a look at it, and we're going to be able to understand what's going on. We're going to be able to not just take a look at it in code, we're going to also be able to take a look at it in the visualization as we're thinking about this, as we're running the code. And this was built by Andre Karpathy. And it's just a really great starting point. So as we get into more application-specific stuff, we're going to start with NanoGPT, and we're going to see how do we take something that's still pretty base level, decode the logits, do some different sampling techniques, and really understand temperature at a deep level. That's the focus of our day today. Wiz, show us how it's done in code.
Oh, yeah. Okay, so this is a lot of fun, but it's also going to be a bit of math. So hopefully you're into math. And I will replace the current share and share, and you should be looking at the collab. Yes, you are. Perfect. Okay. So number one, there's a lot going on in decoding. So this is why we're dedicating, some time to it. as Greg's already mentioned, we're going to start with kind of the basics, the essence of decoding, and then we're going to get a little bit more complicated as we go on. So first things first, we need only a few requirements. Colab comes with the rest of them. We also need to grab the NanoGPT implementation from Karpathy's repo, and then we can go in and start generating tokens. So even that's it. We're already decoding some tokens. So I'm just going to make sure that I'm in the right version of the notebook here, and we get init from init from GPT-2 XL start. What is the answer to life, the universe, and everything? We're going to indicate how many samples we want and how many new tokens we want. We load up the model. We do some shuffling to the GPU, and then we generate from the text. So the idea is pretty straightforward, right? We pass in some text and we get back some text. However, under the hood, we know the model's just numbers all the way down, right? The model never looks at text, right? It just looks at numeric representations of text. So how do we actually get inside it? Well, what we're going to do is, number one, there's an activity where you're going to look at the visualization, so you get to see NanoGPT in all of its glory. Leave that for you guys to play with. And then we're going to talk about how, we pass in text, we get text back, but how do we actually do this? And this is where that kind of idea of auto regression comes in, right? Stealing a term from older models. We're going to basically just keep adding to the sequence, right? So we're going to take our initial sequence, which is going to be converted into a sequence of tokens, and then we're going to predict the next token. And then we're going to pass in that new sequence, so our base sequence plus one token, back into the input of the model. And we're going to keep doing that over and over and over again until eventually we have a model or an output, a prediction. So how do we generate this single token, right? And it's sometimes fun to discover that LLMs are just next token prediction machines, which I say a little bit tongue in cheek, but really it's true. So this idea that we have this function which just calls our model over and over again with an ever-growing sequence in order to produce the next token. So there's a lot of code, but we can understand it. I believe in us. So for blank in range max new tokens, which means we're only going to get up to a certain number of tokens, right? So there's a max max number of tokens that we care about. We're going to do some cropping if it's too long. This is something that we haven't talked about yet, but it is important to consider, right? When we have our sequence, we've talked about in previous sessions this idea of something called a context length, right? Which is how much context can the model handle at once. We've given this just a number before, which has been max seq length, right? So max sequence length. Well, the max sequence length actually contains the total of the input and the output. In this case, right, our input's going to be just one, or n number of tokens, and our output's going to be one. But if we get to a bigger sequence, right? So if we get to, let's say our max seq length is 512, right? And let's say we get to 514. Well, what we're going to do is we're actually going to only consider the last 512 tokens in the sequence, right? And we won't even care about the first two. And this is this kind of idea of what we're doing. Okay, so we take our sequence and we make sure that it's the right size. Once it's the right size, we're going to get back some logits. Once we get some logits, we're going to do some computation. As Greg said, this is division with our temperature. And then we're going to potentially worry about this top K thing. And then we're going to get some probabilities from our logits. And then we're going to pick one based on our sampling method. And then we're going to take the original kind of sequence, and we're going to add the next token, the one that we predicted, and then we're going to return it. You'll notice that even though we have the conditional sequence here, we append to the total sequence here. So we always return the full sequence, even if we don't compute the full sequence. Okay, so we got one of those steps, which is what is a logit. Greg's already talked to us about what logits are. They're just scores, right? It's like the output of attention is just a scalar score. Logits are the same thing. They don't mean anything in a vacuum. They're just these scores that have been computed by our network, and then we convert them to a probability through the magic of softmax. But before we do, this is where we have this temperature thing. So temperature is just how hot are those logits. That's all temperature is doing, right? We're very, very cool logits are going to look a particular way. Very, very warm logits are going to look a separate way, and so we call this temperature just to be fun, I suppose. If our temperature is 1, that means that we don't modify our logits at all, right? 1 is just like whatever the model said, that's what we're going to go with, right? Because we're not dividing by 1 famously doesn't do a ton, right? So we just wind up with whatever we put in, and then we do the softmax, and we get our scores back. Then, of course, what if we made temperature low? And as Greg pointed out, we can't make it 0. This is just a division operation, so 0 is out of the question. You'll notice that we go from like this nice array of 6, 2, 7, 0.1, 8, 9 to this absolutely absurd array of 60, 20, 70, 1, minus 80, 90. These numbers are huge. And what winds up happening with the softmax, you'll notice that like we have this e to the minus 2, right? Which means that the numbers are not super small. We get to this situation where some of our values of softmax wind up being extraordinarily small, which means that whatever the highest one was, right, is going to be as close to 1 as it can reasonably be while still adhering to the rules of softmax. So you'll see here that our 9 logit has entirely dwarfed the distribution. If we sample from this 1,000,000 times, we expect to get this token about 1,000,000 times. So that's the idea of low temperature, right? A low temperature is kind of saying we're definitely going to go with whatever the model said the maximum was every time. That's it, right? That's how you can think about low temperature. People will use this to produce more quote unquote grounded and less diverse outputs because they should mimic things that we trained the model on more reliably. And then we have a high temperature. High temperature does a very fun thing. So because we're dividing these logits by a big number, they get small. Because they get small, our final distribution looks very similar, right? So we have very little difference between our 6, 7, 8, and 9 token, right? So you can kind of see the idea here is that we have this samey distribution, right? It's approximating a uniform distribution, which means that if we sample it, we're going to get a more diverse number of tokens from the output. This is going to allow the model to be quote unquote more creative, right? Which is it's going to pick tokens that might be surprising sometimes based on the training distribution. And so this is great for those kinds of applications. You can see that when we do our kind of like very high temperature generation here, with temperature of 100, we get what is the answer? Life, the universe, everything. Have any prominent clerics yet responded? They have. Religion, communist, Keith Nearer considers, though keeps religion contained. Nonsense, right? Total nonsense. It's basically just picking tokens at random. The output, if it's so high, becomes nonsensical. All right. And then we have the question you'll have to answer: why is softmax so important for decoding? And then we have a bunch of other decoding strategies. So these decoding strategies are fun, and we're not going to get into this script implementation, which is just overriding the generation script from the repo. We're just going to quickly talk about what's happening. The vanilla sample is basically just, we sample whatever distribution we get. That's what we're going to do. There you go. Greedy decoding, Greg talked about, right? We just pick the one that's the most likely next token. That's it, period. If we do this greedy decoding strategy, we will always choose whatever the model thinks is the next token, no matter what. There is no chance we ever pick anything but the most likely token. This is great. Greedy decoding is great because it allows us to have a relatively deterministic, as long as we're on the same hardware, in the same instance, et cetera, it lets us have kind of deterministic outputs, which is not usually true of LLMs. But it's just going to do whatever the model says it should do. We get these things that are sometimes extremely repetitive. That's fine, because we have the ability to penalize repetition. So because we know what tokens have been generated and what tokens we are thinking about generating, right? We can kind of play with that a little bit using human-built rules. This is kind of going to be how we segue into guardrails, right? Repetition penalty is almost a kind of guardrail, right? Where we have this idea of saying, well, we don't want the output to like just say the same thing over and over again. We don't want to produce the same token or sequence over and over again, right? That would be unideal for us. And so that's what repetition penalty does. It checks to see, have we already generated this token a number of times? Then maybe we should skip that, go to the next one, right? So that's what we do. And again, we get the same kind of response, except our output is not just repeating itself over and over again, right? Which is great. That's what we wanted it to do. Then we have top P, nucleus sampling. This is for you data scientists out there. We have finally have another sampling method. The basic idea is we're going to do a smarter selection by saying, let's only choose out of the tokens that cumulatively are like 80% most likely to be the next token. So what that does is it lets us sample for more creativity and variety without reaching into the dregs of our predictions, which might be super wrong. So at the very high temperature, without top P sampling, right, we might choose like a completely off base token. With nucleus sampling, we might choose a slightly off base token. And that has a compounding effect as we move through the generation, where we're going to be more coherent in our generations. So this is things like choosing the word awesome instead of great, instead of choosing the word cat instead of great, right? Which is very, very potentially different. You'll notice that we choose a very high threshold. This is basically just because it works great. That's why. And then we have, so then we do this is the code implementation, very straightforward. All it does is it groups stuff, and then we choose from the stuff that it grouped. See it in action. We see the generation is actually okay. One possibility is that they have a unified wide perspective that allows them to think in general. If that's the case, individual's life might seem like nothing but one tiny drop in a vast ocean of universe. But if it's not the case, the answer is still far from clear. It's definitely more. It's closer to an answer to this question. This model is old and small, and it still does okay. Thanks, top P. Okay, and then we have one of the more favorites, which is going to be we do the top P with temperature, right? So you'll notice we still get this very repetitive response with the low temperature with high temperature. It may come according to new developed theory, which can solve mysteries that physicists are seeking to resolve about why we're here, the big question. So even though we have super high temperature, our response doesn't immediately devolve into some gibberish, right? We get things that are related in some way to the meaning of life, the universe, and everything, which is dope. Our final generation or decoding strategy, right, is going to be beam search. Beam search is basically saying we're going to try a number of different things where we're going to see what the best total sequence is. So it's close to closer to greedy than some of the other methods, though it can be combined with all kinds of methods. And the idea is, again, we're just going to see, we're going to try a number of sequences, and then we're going to choose the one which scores the best. So which has the most, the highest cumulative probability for each token. And this is beam search. It is slower than all the other decoding strategies, but the idea is that it should hopefully be better, right? It should hopefully get us better generations at the cost of speed by seeing, 5 or 6 different sequences and which one scores the best. Okay, and that is that. We have a question here, a discussion question, which is the best decoding strategy? And if you don't know a clear answer to that, discuss with your group. Put some pros and cons, and we'll leave that to you guys to discuss in the breakout rooms. With that, pass you to Greg.
All right, so let's go ahead and hop into breakout rooms and talk about how to take this nano GPT model, get these logits, predict the next token. And guys, this is the sort of 101, right? So in the second half of class, we're going to show you how we can actually take some of this to the next level, how people are doing that today. Just like we did with attention, we're going to kind of take to the next level with the sort of flash attention equivalent, what people are talking about today, how we're taking our decoding to another level to make it even faster. So, try to learn the basics while you're in there. Spend as much time as you need to really grok temperature, to really understand how logits are, scaled by temperature, and then a softmax comes in, or then another decoding strategy comes in. This is really the key. If you can explain this, there's a lot of jobs that you'll potentially get as a result, and there's a lot of value you can create for your team just breaking down this simple idea of temperature to people. So hope you guys have fun with the discussion. We'll see you back in 20 minutes for a quick break before the second half. See you back soon. Okay, back from our quick little break it out, shake it out. I want to zoom in on a couple of potential interview questions for those that might be interested in doing some interviewing. Something like, what does the temperature do in an LLM? That could be a very common question. Or what do logits represent? They might say logits as well. And just let them say it if it's your potential future boss. Don't need to correct them. And people say it all different kinds of ways, depending on where you are in the world. But logits, yeah, it's like, okay, so let's get into speculative decoding. Let's speculate a little bit on what the state of the art in decoding is and kind of recall that we're rooted in this transformer architecture. So, we have from the original BART paper here, or like the original attention is all you need paper. We have the bidirectional encoder, not so much of a concern to us right now. Rather, we're more interested in this autoregressive decoder. So this little token here, this is the sort of start of sequence token. And then we're sort of, predicting A, and then we have A come in, and then we predict B, and then we have B, and then we'll predict C based on that, and we'll predict. And so we get this auto-regressive, next depends on the last, causal, the thing causes the next. And so we're predicting the most likely next token with this decoder, this auto-regressive decoding, right? So this is the whole thing that we're doing, okay? And so there's lots of ways to visualize this, and we've seen all of them. And so now what we're doing is we're saying, okay, we're actually going to do something a little bit more complex here. We're going to take autoregressive decoding, and we're going to take the classic, and rather what we're going to do is we're going to do what's called speculative decoding. So we're going to efficiently draft multiple tokens. So this is a quick drafter down here. And the drafter is going to attempt with sort of an approximate model, sort of a little surrogate modeling action, how we might say this is the next token. And the efficient model is going to be like smaller, it's going to be more performant, it's going to potentially be right, but not definitely be right. And we're going to use this sort of bigger model as a verification model in parallel. And by doing this, what we end up kind of getting a little bonus on is the amount of like actual inference time it takes for each token, if the efficient drafter is right a lot of the time. And this is not sort of a new idea. It's sort of a long history. There was a great survey paper that came out recently, and I know this is hard to read, but the whole point is like there was sort of this original idea in 2018 on this blockwise decoding. And this idea of speculative decoding really came about in 2022, in March of 2022. And there's been a lot of stuff since then, and and rightly so, because it might save people time and money, and that's great. Now, this paper right here is the one we want to focus in on, proposing the concept of speculative decoding. And so the idea here is that we have, this is sort of the paper from March 2022. The link will be in the slides here. We sort of have the spec drafter. This is the two innovations of the paper here. And then we have sort of the spec verification. And the drafter does exactly what we saw. It drafts. So it's specially optimized for, efficient, accurate drafting. And then the spec verifier is just trying to make sure, okay, yeah, that's legit. And so we can kind of visualize this just like from the paper. This is the exact figure, top line on the paper, where we're just really kind of doing this simple idea in parallel. We're not just going to decode. We're going to draft, and then we're going to check. So the small model produces these candidate tokens or draft tokens, and the big model just checks them. And if they're good to go and everything's good to go, then we'll just use those. And that sounds great. So, Wiz, I wonder, like, why isn't everybody doing this? It kind of feels like I need to compute more stuff here. How is this actually saving anybody any time if I'm just now using two models to compute instead of one? It's a little bit confusing.
Yeah, and to be clear, we are using more models. So this is a classic trade-off, right? Where we're not actually, it's not just benefit. There is some drawback, and the drawback specifically is that it's going to take more resources to host these models. So the inference will be faster, yes, but we're going to pay for it, right? Which makes sense when you think about it. We're not getting anything from. There's no free lunch, right? So
Yeah, right.
We're paying for it, but it does be fast, which is good.
So like we need more compute to even do this. So
Yep.
how does it save anything? I don't understand. It saves what? It saves what? Inference time, latency. It reduces latency if the drafter is correct.
It is entirely about latency. So how many tokens are we cranking out per unit time? With this approach, we're going to crank out more tokens per unit time, which is for applications that are latency bound, pretty good, pretty
Okay.
ideal.
And so the idea here is that like if we just throw more GPUs at a regular transformer, right, at sort of a regular kind of picking of the next token, there's this bounded limit of how quickly we can actually do inference, of how quickly we can actually do this next token prediction, right? So that's what we're kind of zooming in on and getting out with this speculative piece. I can have all the GPUs in the world, and I actually can't really change how quickly I predict each token. The inter-token latency, I guess, is what we'd be talking about here. Is that right?
Yeah, ITL, a classic.
What a classic. Oh my God, the ITL. So we're kind of reducing ITL in this sort of, we're sort of adding complexity, but somehow reducing ITL. Again, one of these weird little tricks I'm sure we'll continue to see the field use more and more of as, we're constrained by GPUs, we're constrained by the transformer architecture, and the whole thing matures together. This is exactly the kind of thing that, I think we're looking for when we look for research that is like useful and potentially quite valuable to companies. So yes, it needs more compute, but if we get faster intertoken latency, then hey, like maybe people are happier and it actually makes us more money in the long run if we have a
Exactly.
properly scoped product.
And as we enter into this world and this paradigm of test time compute, right? So, which is inference at time of generation, latency benefits are huge. They're quite, they're quite powerful. They're quite useful. So that's something to keep in mind. Peter asks a great question here, which is, does the drafter use the same decoding strategy? It does use the same decoding strategy. We'll talk about it when we see the code, but yes.
Yeah. Okay, cool. So then there's another piece to this puzzle that we want to add in here. We don't want to go off the rails, right? I mean, we've all heard stories and seen the LLMs, just like bad things can happen if you let the LLMs go off the rails. And actually it's quite simple, as we've seen. If we wanted to intervene in this process of generation, we have the softmax, sort of layer, right? Where we're kind of doing the pick the next token. But we could kind of look, as we do in beam search, we can kind of look and then be like, nah, like we might be like, oh, no, you can't say that, LLM. And if you select that token, you can just programmatically say, oh no, unacceptable. Or the simple sort of idea of a repetition penalty. Don't be saying the same thing over and over, because people don't really do that, except for very, very specific cases. These are simple examples. And so, a more complex example might be something like, there's a lot of fine tuning of LLMs being done to, be able to interact well with other APIs and applications using something like a JSON format, specifically using JSON format as an output to engage with another API. And so, if you have a specific type of output that you want, one way to get this is you do some fine tuning. An even easier way is to just prompt and just say, give me JSON output all the time. But if I'm like OpenAI or I'm one of these big model providers and I tell my customers, like, whenever you call our specific model, you're going to get valid JSON, then I need to make damn sure that they do get valid JSON. And so you can imagine just doing a little check at the end, is it valid? So one of the big things that's happening when we're building applications today is something called function calling. So this is something that OpenAI came out with June 2023 through their API. This is something many open source models have done since. And even there's open source leaderboards now for function calling and how good these models are at function calling. And OpenAI has even put out something that goes beyond function calling and is even more generic and is, something that is called JSON mode. And it literally does exactly this that we're talking about. Because when they used the instruction in the prompt of always return JSON, it worked pretty good, but it didn't work all the way. And so, these are things that came about last year and have been becoming industry standard things. And this idea of valid JSON, if we look at the whole stack of the way we actually build production LLM applications today, I just want to focus in on one little box here called validation. And you'll notice that in the validation box, if you really squint in and kind of look there, you'll see tools like Guardrails, which is actually a company that makes tools. And a lot of companies are doing this now. This is from, again, 2023 here. And so, Wiz, I just want to have a quick discussion on this here. When we think about valid outputs, when we think about Guardrails, what are some of the state-of-the-art tools that people should be thinking about, should be looking at? Is there an answer to this today? How can we make sure that we are, producing valid or good or correct or high quality, or let's call it dope results? Is there like a way to do this today?
Kind of, yeah. I mean, so it comes down again to this idea of what, we can certainly get very close thanks to things like guardrails, thanks to things like I mean, there's too many tools to count these days, but there are a number of libraries that do this, there are a number of models that do this, there are a number of libraries with their own model that do this. We can get very close. Just use guardrails or MetaGuard, right? Like Llama has shipped MetaGuard the last 2 or 3 releases of their models. It's I would say finally starting to get close to usable. And so something like Llama Guard is useful if you're in the open source world. If you're not in the open source world, you're probably looking more at something like guardrails. Both the library called guardrails as well as there's other companies that offer these things like the Nemo microservices guardrails from NVIDIA. There are a number of people whose sole job it is to verify that outputs of LLMs are not bad as you define bad.
Yeah. Yeah, and this is something that also, you end up working with your customer on too, right? I mean, you sort of get feedback from the customer. You sort of say, okay, how can I modify the way this is operating in general? Maybe do that with a small rollout first before you go sort of giving this out to everybody in your entire network. It sort of goes back to classic product development, like do the tests, make sure it's good, make sure it's sufficiently constrained, and make sure that nobody's going to get super pissed off and your company's actually going to lose way more money than they're going to make, right? It's like business 101, product management 101. Okay, so when we talk about then speculative decoding and guardrails, you got a little demo for us today. But one of the things from the demo that is particularly interesting is you're not going to use the libraries that we'll potentially be able to use later, right? We're going to kind of do this a little more raw with the Nano GPT setup. I'll let you talk about that more as you get into the demo here, but I think it's important to note that it's not actually this difficult to apply some of these tools today in practice. We're just down in the weeds today with the whiz, doing speculative decoding and guardrails. Over to you.
Yes, okay. Just gonna also touch on a few questiones in chat. So we have this let's say we have an API. We ask the LLM to output code that conforms to that API. Is there a way to outline? Yes, that's what something like guardrails can do, right? So guardrails can, if it understand, like if you can describe what your output needs to look like, guardrails can help it look like that, right? Because we get to choose what the next token is. And if it disobeys a rule, we can say, not that token, until it obeys the rule, or until we insert our own token that obeys the rule. And we'll look at that in just a second. But for right now, we're going to talk about speculative decoding. The implementation you see in Colab is absolutely not the implementation that you're going to see in the Transformers library. This is just adapting Nano GPT to use speculative decoding. We don't have a training stage, and we aren't crucially taking advantage of parallelization, which means that this version of speculative decoding doesn't offer a inference benefit. So we typically would go through this in a multi-stage process whereby we train our draft model to get better at our task, which we can do quite straightforwardly through libraries like Transformers and Hugging Face. But just to see underneath the hood a little bit on what the actual process looks like, we've written some extremely fun code for you guys. You'll notice that we have these basic kind of things, right? We draft tokens, we verify tokens, and then we pick which tokens to use. There you go. So first things first, we have this initialization. We're not doing much. We're just setting up some models, loading them up. We're going to cheat a little bit here, and we're going to use GPT-2 as our drafter and GPT-2 medium as our verifier. Technically, these are trained on the same objective, though we have not trained our draft model on the drafting process. So this will result in fewer tokens being accepted than if we had trained it on the drafting process, which makes sense in some way, right? We want to get good at not predicting which token comes next according to the distribution that our draft model knows and understands. We want to get good at predicting which token comes next based on the distribution of our verifier model, right? So that's why we need a training step there. We have then safe model outputs. This is just code so that we don't blow up our memory. Then we have generate, right? Where we're just going to go ahead and we're going to generate some tokens. You'll see here that we generate many tokens up to the point of our draft limit. If we exceed the limit, we stop doing this. And then we move to verifying. You'll notice that this draft sequence is what's being verified, right? So what that means is that we want to give our model, right, the sequence that we've attempted to create, which in this case is going to have like n number of tokens in it, right? And then we're going to see if that aligns to the predictions of our base model. Though we are not going to auto-regressively generate at this step, right? Which is how we're getting that savings. So we auto-regressively generate a draft sequence, and then we do one verification step on that sequence. If everything shakes out such that our probabilities are within whatever parameters we set, then we use them, and if they aren't, then we don't use them, and we instead get a new token from our verification model. So we allow the verifier to produce the token instead of our draft sequence. You'll notice here that we have some more error handling. Running it is very straightforward, right? We just create this decoder, and then we generate tokens, and then we choose which we get. In this case, you can see here, we get the final result. What is the answer to life use of everything? How can we eliminate the need for what is the answer to life use of everything? How can we eliminate the need for the generation is not great because we're just using GPT-2 medium. But you can see here that we accepted 3 of the 7 potential draft tokens. Go team. So we were able to save some time, quote unquote, by using the draft tokens. And the whole idea here is that this is kind of going to leverage something we're going to talk about much later on in our time together called distillation, right? This is kind of a distillation process where we're teaching this small model to be really good at talking like this slightly larger model. The size difference between them, as well as a number of other optimizations afforded to us by appropriate parallelization and model loading, make this just faster most of the time, assuming that your drafter is high quality, as in it more often than not produces tokens that we are going to keep. We do get some savings even if we only keep very few, but obviously there's a threshold at which this becomes cost effective. One thing as well that we want to keep in mind with speculative decoding, this is extremely good for latency bound applications, as all it does is increase latency by spending more resource, right? So if you're in a hardware constrained environment or resource constrained environment, we're not going to use speculative decoding because it's going to cost more resource. But if we have the resource and we just need that model to crank tokens out as fast as humanly possible, or I suppose non-humanly possible, then we're going to use speculative decoding. Okay, last, but certainly not least, is guardrails. We actually already kind of did guardrails right earlier in the notebook with repetition penalty. We're just going to apply some heuristic to token generation. Things like we don't want to do, we don't want to include some tokens. You'll notice that we can do this at the actual token level. So we can do this as part of the generation process, whereby we just mask the logits. We're going to give them, in Python, the very lowest value, which means that there's no way that they will be representative in your sample through softmax. Basically, this is like dividing by an extremely huge number, but only for this one particular logit or these targeted logits. We technically can do this post or pre token generation. So we can do this after we generate a token, but we're going to try to do it as we generate the tokens because that's going to let the model generate more naturally. We're basically going to use a manual process to interrupt. Model, don't say that, instead say this, and then let it carry on with its task. If we do something like just change the token after the fact, the underlying distribution is still going to act as if we've used that token, which is going to potentially move us into a space that's undesirable. For instance, if the model uses profanity and we really don't want it to, it's likely that the model is going to generate additional profanity in the future, especially if we don't actually remove the profanity from the sequence that it's autoregressively generating from. So guardrails are incredible. Remember, because we are plugging the sequence together token by token, right? We can just, anytime we see a token that we either like or don't like, we can interrupt the process and do something with it. This is how we do things like creating functional JSON, right? If we know that JSON must adhere to a certain pattern and we generate a character that is invalid JSON, we know it will break the JSON. We instead tell the model, hey, don't do that, right? You got to generate something that doesn't break this sequence, and that's the idea. When we actually do the generation, it's extremely straightforward. We just straight up get in there and we change things directly. There's all kinds of different fun ways we can apply this, right? If we want the model to be sing-songy and happy, we can tell the model to favor tokens that fall into those categories, and etc. We can make the model or force the model to use some specific token instead of some other token. Places that guardrails are most commonly used, especially now, things like PII redaction, that can happen on the input or the output of the model. What we're talking about is just output guardrails, and then some others as well, which you can discuss in your group. Set up tokens, that's it, and then we run it, and we do the generation, and it runs, and it generates, and we get this generated with block words: war, conflict, fight, and battle. We see the future of international relations will be characterized by, and we do not get the tokens war, conflict, fight, or battle in our generation, which is nice. And it's not just skipped as in, eager to engage their own countries in this vital war task. No. It just doesn't ever act as though it generated that token, allowing the generation to remain as natural as it can when you're using a smaller GPT model. With that, pass you guys back to Greg to get into our last breakout room of the day.
Yes. Okay. So speculative decoding and guardrails. So guardrails is also a thing that you might definitely be asked about in sort of an interview capacity. Maybe think about what your answer would be to like explain guardrails and like how do they work and why should we trust you with our models and with our data kind of thing that you might get in an interview today. And so as you go through this, think about some of the things that you want to be able to answer: temperature, guardrails. Less likely to get asked about decoding specifically, but if you can answer these things in really clear, specific language, then this is going to be something that gives you a huge leg up versus other folks in the industry interviewing for the same position. So this is something we hear all the time. Get your reps in your breakout room, and you'll be in better shape heading out into the real world instead of the classroom setting. Okay, guys, let's go ahead and get into it. This is the last breakout room. We're going to do 15 minutes. We'll come back and we'll wrap. Make sure you can fully understand the meme we started with, and we have some takeaways for you before some feedback, and let you know what else is coming up next. All right, 15 minutes. We'll see you guys back. Have a good time, guys. We are back from breakout room number 2. Now, at this point, we can start to conclude a little bit. So this is where we sort of end our journey with the inside super guts of the transformer, and we start really learning about how to leverage and apply them and tune them and tweak them to our liking. This is going to start on Thursday, and all of these fundamentals are never going to change. What we talked about today is we talked about next token prediction. It's all about decoding those logits. Logits is looking at the log of the odds that we're going to predict this token or that. Temperature helps us scale those logits. Low means it's going to be more predictable. High means it's going to be less predictable. And there are different decoding methods. You can do a quick Google search. Turns out greedy sampling is pretty good, pretty solid, and pretty straightforward. We can do things faster if we have more compute and actually decrease ITL with speculative decoding. It's happening more and more. This is something you can sort of bring up that's quite state of the art in conversations with people today. And guardrails are the ever present important topic for enterprise. So definitely something to bring up if you're looking to be listened to or to be heard in a context with enterprise leaders. So, hopefully you got the nice tour de force of the transformer and you guys are sitting in a pretty good place. We'd love to hear what you thought about today's session. All right, thank you everybody for the feedback. We've got a couple questions in the chat I want to go ahead and just get to real quick. First one looks like, would we be looking into how to handle non-English prompts and requests from users? What do we do with non-English?
Yeah, so anytime we are looking at something that isn't English, we're largely just going to depend on the fact that we're using multilingual language models. So for the basically the entirety of the course, any model that we use is going to be decently multilingual. The way that it works under the hood, if in case that's the question, is that the model has some non-language aligned internal space, and then it can decode into a number of languages from that space. So think of it as in someone who speaks both fluent French and fluent Portuguese. Their brain's internal representation, the actual thought that occurs, that isn't necessarily bound to a single language. Doesn't have to, you don't have to think in English. You can think in shapes and think in colors and this. So that's the internal representation that you then decode back into whatever language your target language is.
Yeah, do LLMs think in images? Do they think in words? Do they think in sounds? Are the robots going to think in tastes? I mean, who knows what the future holds? Everybody, thank you for joining us today for session 5 on next token prediction. Now, next up in the next module, we're going to start covering training, fine-tuning, alignment, and we're going to start with unsupervised pre-training. We're actually going to connect what we learned today, Logits, into the way we actually train models with something like cross-entropy loss. There's some tight connections there that we're excited to get into as we start to get into unsupervised pre-training and exactly how GPT-1, 2, and so on, all the way up to the state-of-the-art models today, are built for production. We look forward to seeing you on Thursday for session number 6 on unsupervised pre-training. Have a great week in the meantime. Hopefully we'll see you tomorrow on YouTube Live for AG2 with the creators live. Have a great night, everybody.